To find life beyond Earth, astronomers look for a specific region around a star. It's called the Goldilocks zone, an orbit where temperatures are mild enough for liquid water to remain stable on a planetary surface. This single metric of orbital distance has governed the search for life across the roughly 4,000 exoplanets discovered by our telescope so far. But focusing strictly on the orbit leaves out a massive physical variable. A planet's potential for life also depends on the host star's location within the larger structures of the Milky Way. The galaxy functions as a collection of distinct continents, each carrying a unique history of star and planet formation. Finding a just right orbit is insufficient if the star itself was born in a neighborhood that lacked the necessary ingredients for life to begin with. To understand these galactic continents, we have to view the Milky Way in 3D to analyze its core architecture. At the center lies the bulge, a dense mass of ancient stars surrounding the galaxy's supermassive black hole. Enveloping the structure is the halo, a massive, diffuse sphere of hot gas and dark matter. Closer to the center is the thick disk, a wide vertical structure containing older stars from the galaxy's earlier eras. Finally, there is the thin disk. These narrow, spiraling arms contain the galaxy's youngest stars, including our own sun. These zones represent the different neighborhoods where stars and their potential planets are born and evolve. Planets form within the dense disks of dust and gas that rotate around newborn stars during their infancy. Forging a rocky, Earth-like planet requires heavy elements like carbon and iron. The ancient stars in the halo and thick disk formed in chemically poor environments, whereas the younger thin disk is rich in these heavy elements. New data from the Gaia and Kepler telescopes has allowed researchers like Jesper Nielsen and Jesse Christensen to map where planets actually live across these zones. Simulations prove that gas giants and super-Earths are nearly non-existent in the old, turbulent neighborhoods of the galaxy. The thin disk acts as a galactic habitable zone because previous generations of dying stars seeded it with the building blocks of worlds. Habitability requires a specific nesting of conditions, a stable orbit within a chemically rich star system located within the thin disk. This shift is turning astronomers into galactic demographers who can predict planet populations based on the history of their neighborhood. The Nancy Grace Roman Space Telescope will soon survey these neighborhoods with a level of detail that was previously impossible. Our sun is located in a sparsely populated suburban zone of the thin disk, a position that may have been a prerequisite for our existence. Determining whether life is an inevitable result of galactic geography or a rare miracle depends on understanding these specific corners of the cosmos.